Hello, welcome to the presentation of my algorithms course homework 9. In this homework I will solve problem related to dynamic programming, which is a programming paradigm used in algorithms. So now let's start with a basic practice question on dynamic programming. Okay, so it gives a problem which is a Fibonacci sequence, which is a fundamental example of dynamic programming. It's not an actually dynamic programming paradigm, but it's a really good example in order to understand the logic behind dynamic programming. So the Fibonacci sequence is defined as follows. It defines the Fibonacci sequence, and it asks me to write a dynamic programming function to find the nth Fibonacci number efficiently. Our function should take an integer n as input and return the nth Fibonacci number. For example, for Fibonacci 5, the output should be 5. For Fibonacci 8, the output should be 21. So it asks me to transform the main Fibonacci function, which is used in recursive functions. You can implement Fibonacci sequence with a recursive function, but in this case it asks me to transform that recursive function into a function that uses the properties of dynamic programming. So I'm going to stop the video here. I will implement the function. I will come back with the function. Okay, now I find a solution for this problem. So in this solution we have a Fibonacci function, and we are checking it by if-else statement, and it calculates correctly the number that is given as parameter to the function. So now let's see if it's correct or not, and then if it's correct I'm going to explain you the solution I did. Okay, so the ChatGPT says that my implementation looks correct. So I used the Fibonacci sequence fs to store previously computed Fibonacci numbers, blah blah blah. So it says that it's correct. So I'm going to stop the video here, and I will show you the solution. Okay, so before moving on to our solution, I want to show you the naive approach of Fibonacci sequences. And most of the times the programmers or the implementation of Fibonacci sequence is made by recursive functions. So here's an example of that. So we have an if statement checking whether the number is greater than or equal to 1 or not. In that case it returns the number, because if Fibonacci is 0, it will return 0. And if Fibonacci, let's say we are calculating Fibonacci 1, it will calculate 1, because this is the property of Fibonacci sequence. In else statement it calls it recursively like this. So when we look at the time complexity of this naive approach made by recursive calls, so if we say that the total time complexity of function Fibonacci of n is T of n, so the time complexity is going to be, we have a return statement here, so O1 plus, and we have two recursive calls. So if this is T of n, then this is going to be T of n minus 1 plus T of n minus 2. So the total time complexity is going to be O1 plus T of n minus 1 plus T of n minus 2. But in our new function, which is made by using properties of dynamic programming, the time complexity is totally different. So I'm not going to explain you detailedly. I will explain it later, but let's see the time complexity. So we have a return statement O1, and these two statements are actually again taking time of O1, and we have another return statement O1. So we have 3 O1 and we have a for loop here that iterates through the array for n times. So the time complexity comes from this for loop is O(n). So the total time complexity is going to be T of n equals to O(n) plus 3 times O(n). So if since we are working in worst case, the total time complexity of this function is going to be O(n). But we had T of n minus 1 plus T of n minus 2 here, which is a more complex time complexity. So by using dynamic programming, we get a result that works faster than our, the fundamental or naive approach of Fibonacci function sequences. So let's check out our function. Okay, so in the beginning, just like we did in our previous approach, we are starting again, checking whether the number is smaller than 1 or not. In that case, it will return that number. So in else case, but in else case, we have a different approach. So in else case, we have a list called Fibonacci sequence, and I abbreviated it as FS. So in this list, we have actually n minus 1 zeros. For example, if our n number is 5, then this list is going to have 6 zeros in it. And then we are assigning the element at index 1, which is 0, to 1. In this Fibonacci sequence list, we are actually trying to store the values of each iteration in a Fibonacci sequence. So, and then we have a for loop here, works in range of 2 minus 2 n plus 1. Why we are starting from 2, which is index number 2? Because we have already declared the numbers at index 0, which is 0, and index 1, which is 1. So we are starting from range 2, and then we are going to store the values that corresponds to that number in the sequence list. And in that case, we are actually putting that element, actually changing that element, which is initially 0, because we have already declared it as 0. And this list has a size of n, so it will store all of the necessary elements that is needed to calculate the correct answer for Fibonacci n. So in that case, we are changing that 0 with Fibonacci sequence I minus 1, which is Fibonacci 1 actually, and Fibonacci 0 plus Fibonacci 0. So we are changing the number 0 with the number that corresponds to this equation. So we have used the Fibonacci sequence property, and then it's going to return Fibonacci sequence n. For example, if or now let's say we are trying to calculate Fibonacci 3, so we have put the number 0 in the first index of the list, and then we put 1 in the second element, which is the element at the index 1, and we have changed it with 1. And then in this for loop, we are starting from 2, and in the first time we are calculating 2. And a Fibonacci sequence 2 is actually Fibonacci 2 equals to Fibonacci 1 and Fibonacci 0. So Fibonacci 1 is 1 and Fibonacci 0 is 0. So Fibonacci 2 is going to be 1. And then the for loop will iterate through the next number, which is 3. And the for loop will end here because we reach to our destination in this range. So Fibonacci sequence 3, Fibonacci 3 is equal to Fibonacci 2 and Fibonacci 1. So Fibonacci 2 is 1 and Fibonacci 1 is 1. So the Fibonacci 2 is going to be 2. Since we have ended with for loop, the else block has ended, and then it will return a Fibonacci sequence n as 2. So Let's see some other properties of dynamic programming in this function. So the first thing is actually you can see that we are storing the values that we have calculated for each iteration in this for loop in a list called Fibonacci sequence. So this is needed for dynamic programming because in dynamic programming we are trying to divide our problems into subproblems, just like we did in divide and conquer approach. Then we are storing that value in each time in order to use it for the next calls. So that's what we call memorization. As you can see, we don't have that property in this Fibonacci function, because let's say you have to calculate Fibonacci 4. In Fibonacci 4, we have to know Fibonacci 3 and Fibonacci 2. Let's say you have already calculated Fibonacci 2. It doesn't matter, because each time the function calls it recursively. No matter you have calculated Fibonacci 2 previously, it won't use that Fibonacci 2 because it will not memorize it. Why? Because it doesn't store it anywhere. For example, you have called Fibonacci 4 and you call Fibonacci 3. In both cases, you have to calculate Fibonacci 2. So if you do one of them more previously, it doesn't matter. You have to calculate Fibonacci 2 again and again, no matter what, because it doesn't store that Fibonacci 2 value in anywhere. But in our new Fibonacci function that is implemented by dynamic programming, it actually stores that value. For example, in order to calculate Fibonacci 4, let's say, you have to write Fibonacci 4 here, and then it will equal to Fibonacci 3 and Fibonacci 2. But before moving to Fibonacci 4, you have to calculate Fibonacci 3 previously in this for loop, because it iterates for each element and it will start from 2 and it will go until we reach to our goal. So you have to calculate Fibonacci 3 and Fibonacci 2 previously. So if you have to going to calculate Fibonacci 4, you find out Fibonacci 3 and Fibonacci 2, but function is going to say that, oh, I calculated it previously, so I can just put the number in here directly. We don't have that in this function. This is another property of our new function. So this prevents us to do more unnecessary calculations. It prevents the function do the unnecessary and redundant calculations. It just simply stores that value, memorizes it, and remembers it when it called it again. So this is the property, one of the properties of dynamic programming. And another programming, another property of this dynamic programming is bottom to top approach. So bottom to top approach is actually leads to memorization. So what is that? As you can understand it from its name, if you want to calculate Fibonacci 7, actually, you'll no matter how great your number is, we have to start from Fibonacci 2 each time. You first calculate Fibonacci 2 and then Fibonacci 3, Fibonacci 4, Fibonacci 5, Fibonacci 7. So you're starting from bottom and you're going to top. So this bottom to top approach is actually leads to the memorization we just have talked about. Okay, let's use our function on it. Let's see if it works or not. So it's, as you can see, it works correctly. Let's write some other numbers, which is 6 to 5 and 8 to 9, let's say. Okay, so I haven't calculated yet, but I hope that is correct answer. Okay, so this is the end of the solution. Okay, I'm going to stop the video here. We are done with the homework 9. So see you next time.